Thanks everyone for coming in. This is a talk about our journey to try Graph on Aerospike. I'm Athreya from PayPal. I represent NoSQL engineering and architecture team. I have my colleague here.
Hi everybody, I'm Bruce. Currently I'm the architect from PayPal eServe organization. And I was the architect for data platform. Now I'm mainly focused on Graph. Thanks.
We're going to talk a little bit of history and background, and then quickly switch to the main topic, which is Graph. I'm going to have a few slides on that, and then Bruce is going to continue and discuss more on how we did Graph implementation on Aerospike. A quick brief history. This is just a slide to show what we focused on from the beginning. We onboarded Aerospike at PayPal in the early 2015, just as a POC and give it a try, how does it look like, and things like that. And then towards 2016 Q1, we were pretty much ready with a key value use case, which is massive in scale, which we knew that it's going to be that way. So our focus all the way was to harden the system and make it really be able to handle key value use cases. And then we also invested a little bit on building UDFs and leverage the use case, which we had its own journey of learning and doing mistakes and then fixing that and going forward. Now we are in 2019. We started investing into trying Graph on it based on all the experience that we have had and all the great experience we have had. And then towards 2019 Q1, we are in the process of enabling a big use case on that. In terms of key footprint, we started with the small, tiny clusters. We also have very fixed type of designs. It started with 20 billion keys, and then follow on, we had a 5x growth of 100 billion keys, and then again 500 billion. Now we're in this range of a trillion keys in the entire ecosystem of Aerospike. And these are spread across several different servers, about 1,200 servers right now. We are onboarding more, so we're going to be in 1,600 servers. This is the footprint of all the servers and how we grew with that. And we have very fixed type of systems that we have designed. We have not changed any of that. Basically trying to keep consistent. And so the footprint right now is about 9 petabyte physical storage and about 384 terabytes of memory spread across about 64 clusters. And we're also distributed across many availability zones. So that's all considering that we have enabled XDR in some cases. Some cases we don't enable XDR just to make sure that we don't flood our data center cross networks. But data is loaded concurrently from backend offline to the online systems, and they're consumed on the edge clusters. Just to show the focus of how we were starting to design. So the battery indication here is, this is by the way Tesla battery. And the intention here was to really pick up something that can survive all kinds of thrashing and bashing that we were anticipating that may happen on the database. And we designed that, and further with an intention that we will build a battery pack. And then the intention there is to have everything included, so that once we build the battery pack, we should be able to leverage it for many different use cases. So the solutions we put together is also very custom client type of solutions. We built it, homegrown, a specific client, and this is called Sniper. We call it Sniper internally. This can do comparison tests. So it can, in real time, we can spin up multiple client agents, and each of these color lines, in this case it's a blue line versus red line. So that's actually doing a comparison test. And in real time, we can graph it out. So spin up two different clusters. For example, one with certain type of configuration on Aerospike, another cluster with another configuration of Aerospike. Point one client to the first cluster, point the second client to the second cluster, and then in real time watch the difference. Now this helps in many different ways. if we were to do a comparison of hardware itself, which is constantly changing, how do we know what is happening underneath when we change the hardware SKUs? So we validate all of this with this tool. It's pretty fast. We can quickly understand the characteristics of whether it's SSD changes, whether we're looking at memory footprint. So all these SKU validations, that happens pretty fast. And it's repeatable as well. Then we also put together database reporting. Within PayPal, the way we operate is like a horizontal team. We have many different verticals, and we actually act as a service provider. So that means we try to enable our customers with different use cases. While we do that, we also want to have as much data available for them to be able to operate as independently as possible. So with that background, we created kind of a more visibility in terms of monitoring. If we were to put together the entire inventory of clusters for our customers, they can read exactly what is going on within their database by means of these reports. And the reports are structured in different ways, where one of the pages is dedicated for capacity monitoring versus others are dedicated for total inventory monitoring. Some of them are very specialized, like how do you really show keys in all of this, and you need to consolidate everything, put together in a number format. Now these numbers are not readily, there is master objects versus replica objects, but then our customers don't care. They want to know how many real keys do I have. Right? So these reports filters out all of those complexities, basically derives all the numbers from different nodes, consolidates that, and then put together numbers that is easily readable. So that way they know exactly how much capacity they're leveraging, how much they have left. So we can do predictions based on how much memory is left from what is configured, and then work backwards with 64 bytes and know, okay, you can only use the next few million records in this cluster. After that, you're going to be in the warning zone. So then we start sending them alerts up front, so they can manage their databases up front. So we don't really go in between. So basically, if there is any capacity needs, they'll reach out to us. You know what, we're seeing a warning saying you're at 80% utilizations. What can we do, or can we expand? So that's an homegrown solution. Then we also invested pretty heavily in the last 2 years on database lifecycle management. Basically, all these are Ansible APIs. Each of the lifecycle has been coded into different APIs. For example, if you want to run queries, we have one other API which will be just doing queries. And this is also put together as a Ansible playbook. So you can kick off an upgrade, and then you can go for sleep. If anything is wrong, it'll just stop. So basically, we're trying to speed up and with as minimal human interventions as possible. And we're managing about 1,200 servers right now. Though it's a little bit of still human interactions are still there. We have more sophistications that we need to build on top. We're also investing into building orchestration layers on top of that, which is coming up in the upcoming months. We also had to build auto failover solutions, which is outside of Aerospike. Basically, if we are distributed geographically, also in the AP world, not in the SC world, strong consistency is taking care of a lot of those things. We have a majority of our systems still in the AP mode. Hence, if we do lose nodes back to back, there could be cascaded failures, and we could be exposed to data unavailability for a period of time. So as soon as we detect, we have external applications that's detecting that or monitoring that. And if we do encounter such situations, we trigger a failover. And what that failover is, kind of an application signature, where we inject a signature into the database saying this cluster is not in good shape, and the application reads immediately and migrates the traffic. So the application is also very smart. So Bruce, you can also touch upon that when we're talking on this. So they're built in a way that we can scale horizontally. So the application layer has its own data service where it does not know necessarily where the physical location of the data is. Hence, we simplify our build outs where we can horizontally keep adding clusters after clusters, and the application manages the routing of the calls. And the deployment strategy has been, all right, so we got our battery, which was our Aerospike, we packaged it. Now, whether we put it into a model KV here, it's an X. or whether it's a model X or a UDF here, or it should be a model G. Now what is model G is our graph use case, which is what we're going to talk more about. Bruce. Bruce, take it off.
Hello. So let's start my part. So basically, there are three parts. The first is I'd like to introduce why we want to invest on the real-time large-scale graph database. And the second part is how we design it. And then our roadmap, future capability, right? We want to invest. Sorry. So actually, a lot of domains requires graph capability. So especially for risk, PayPal risk. So if we look at Gartner's, this is fraud prevention capability, right? So at the low level, from level 1 to level 3, it's just discrete data points and analysis. It's simple. But to move to the high levels, right? So we need more and more connected data, linked data. For example, we need to understand, for risk, we need to understand the relationship between two accounts. Right? There's a strong link, weak link. For example, for VID, visitor ID, for the bank account, credit card, phone, right? Those we regard as a strong linkage, right? For address or IP, they are weak linkage. So based on those understanding, we are able to know the relationship, figure out the relationship of the accounts. Those is one example. And another example is the behavior. For example, transaction, right? Based on transaction, actually, it's a transaction graph. So based on the transaction graph, we are able to understand the community of the fraudsters, the behavior, interaction of the fraudsters. Right? Those we can enable us for the advanced risk analysis. So this is a very important capability for us. So to build a graph solution, it's possible that we can build it on top of relational database, or Oracle, right, or MySQL. So the problem actually, the first is the performance. If traditionally we can design in this way on top of Oracle, say for each vertex, it's just one table, and to support the linkage, right, edge, we need to have an index. So the problem is when we traversal the graph, for example, when we traversal to one node and to the next hop, for every key, we need to have a key lookup. You can imagine how many block read we need. So compare with the traditional, compare with the graph solution, right? Basically, it's a node vertex, the vertex-centric design, which means the vertex information and its edge information will be stored together. Just with few block read, we're able to know the next hop, right? So for relational database, it's a SQL join here. Its performance is not good enough. And the next is for SQL, right? It's not a native graph query language. For example, for a simple 2-hop query, if you want to write SQL in SQL, right? It's a little bit complex. So if we need a graph query language to support those traversal query. And the third is for Oracle, right? MySQL, it's well structured. Because our business grows very fast, we can frequently need to add more vertexes, more properties, more edges. So for database, the overhead is too high, right? And for our business, they do ask us to support some complex data types like a list map. So for Oracle, it's very hard to support. And why we need a real-time graph database? So before we have a graph capability, the previous solution is we will have offline graph data processing, and it will have the result. We will convert the result to KV storage and push the KV data sets to production fast KV storage. So our application need to write code to implement the traversal logic. The problem actually is first the data refresh latency. It takes time because it's offline data processing. Usually it takes one day, or 1 week, or even more than 1 week. And the second is, it's for offline data processing, it's difficult without graph database support. It's difficult. You can imagine the join, right, in offline. It's hard. And third is, it's not generic for online application. Online application have to write code, right? Even with small transversal logic change, we have write code. It's not generic. So another is, it's hard for us to apply centralized governance because each solution team will push their KV storage, KV data sets. A lot of data actually are duplicated. But for us, we are hard to stop them, right? They are different teams. So then we know we need a graph database. Then if it's a normal graph database, say if we build the database on top of Cassandra, HBase, the typical latency will be seconds. So it's too long for online application to integrate because the SLA, our SLA is very, very tight. So then the solution will be, okay, the near real-time data processing can leverage this graph database. It's good. However, we still need to convert to KV datasets and push to production. And the application still need to write the code for transversal, right? So it's not good enough. So that's why we need a real-time graph database. So we can share the same graph database for both async data processing as well as the online application. They're the same. Data refresh latency, P99 is just within 3 seconds, right? And because of that, our total cost of ownership can be reduced because we don't maintain the offline, the graph database as well as the faster KV storage. Sorry. And also, so we can enable the centralized governance as well because they share the same graph database. It's very important. And if we look at the graph database landscape, it's provided by Tiger Graph. So there's two interesting categories. One is the enterprise operational graph database, like Titan Graph, Genus Graph, OrientDB, or Neo4j. But they have their own problem. For example, for Titan Graph, Genus Graph, they're mainly based on Cassandra, HBase, BerkeleyDB. The latency is too long. Usually it's a second level, right? So we need to look at the real-time graph category. Since it's very interesting is, if we look at the industry, since 2017, the real-time large-scale graph database solution emerged. The Titan Graph and the GBase, developed by Alipay. Both of them announced that they can support trillions of vertices and edges. And their query performance is millisecond level, pretty fast. So if we look at those solutions, what is common? Both of them leverage fast KV storage as their internal graph storage engine. If we look at then we consider, right, if we want to build the solution, we need a faster KV storage. Look at, if we bring a new fast KV storage in our PayPal, it takes a long time to make it mature for production operation. However, in our PayPal, our Aerospike solution is already available. So that's why we choose Aerospike as a storage engine, as a storage solution. So first, Aerospike is super fast with persistent support, right? Share nothing architecture, there's no single port fill-in, highly scalable, highly available. If you look at in the past year, right, look at the system availability, it's pretty high. And it supports the native XDR. It's very important for us to support MDC. And it support the flexible data types like a list map, which is important for the business. and it supports tabular. Tabular is very important because for real-time graph database, performance is very important. So for the query, right, we directly know what kind of properties, what kind of edge we want to traverse, we want to fetch. So we just fetch those instead of read-write as a whole, right? And another is also very important is async support. So Aerospike support the totally async non-blocking Java client. This is very important. You can imagine, right? For one, like a 2 hops graph query, basically it's possible to access like hundreds or maybe thousands of vertices, right? If it's blocking I/O, then how many threads you need to support a highly parallel data access, right? Data fetch. So you can imagine the cost of the threading, context switch stuff. So with the async support, so usually most of the query engine, just one query, just one thread. So thanks for the async technology, we can make the solution fully scalable and efficient. So most important, all of those are already being proven in production. And this is a comparison for the candidate solution that when we try to build our own solution, right? We decided to build our solution, but we still need to look at our candidate. So eventually we choose target graph and the genus with CLDB support. So I won't go to the detail, but basically we evaluated and we believe our solution will be very competitive. So this is a Milkyway graph. We call our solution Milkyway graph. It's a large scale graph database solution. So before we go to the design, first let's review the design principle. The first, we want to enforce a centralized configuration and manager-driven solution. Schema should be enforced. And it should follow the schema evolution principle, just like a database, right? Backward compatible. And second, we should support the linear scalability. We can gradually invest our storage at a new cluster or new node, right? And we can achieve the linear capacity increase. And eventually we can support trillions of vertices and edge. And we should support eventual consistency. For real-time graph database, to support ACID is too expensive. And for risk use case, actually we are not that sensitive to the consistency, right? So basically, to achieve the eventual consistency, an important update is very important for every write operations. So our data recovery strategy will be very simple. So in case Aerospike crash or the data loss caused by the cluster, right? So we just replay the graph bin log, which is a mutation log, right, at that time, and the data should be recovered, should be fixed. And then we need to look at the graph query language. If we look at the industry, basically there's 3 major graph query language. One is Gremlin. Gremlin actually comes from Apache Tinkerpop, which is one of the top projects of Apache. Actually, it supports both OLTP, OLAP, compute, traversal, and most of the graph database actually support it. So it's the winning graph query language. So we decided to support Gremlin. And we also look at the other solution like OpenCipher. OpenCipher provided by Neo4j. It's open source, but the community is relatively small. And another is GraphQL, provided by TigerGraph. It's more like, it's very interesting, it's more like a programming language instead of a query language. So it's very powerful for MPP, for distributed compute, very powerful, but more like a programming, right? So next is the schema. As I mentioned, right, the high-level principle is configuration manager-driven. So we need to define the graph in configuration. Here's an example, right? for a graph instance, we can define the metadata. It has its own metadata, like version, last modified, description, etc. And then we can define the vertices, like account, right? Account has its properties. And a vertex has its own metadata, like TTL. Right? And then we can define the edge. Currently, we only support the directional edge. It's not a problem for Gremlin, because Gremlin can support from traversal from source to destination or from destination to source. It doesn't matter. Yeah, maybe this is a knowledge graph, for example, this account and assets. Assets can be like a IP, phone, bank account, etc. Right? So, and we look at the property types we can support. We not only support the primary types, we also support the complex type like a list map. And most important, Gremlin supports the metadata for a property, for each property. So we have some default properties like creation time and the last modified time. This is very important to support the idempotent update at each property level, right? Say this operation actually has a timestamp, and this timestamp actually is newer than the timestamp in the database. Then we apply the update. Otherwise, we just ignore it. This is idempotent. And this is our overall architecture design. You can see we are using Aerospike as a storage solution. And on top of it, we support our query engine. Next slides will introduce more about the query engine and the storage engine part. Now we just focus on the data pipeline. So we integrate with our events messaging system, real-time messaging system, and we consume the message and convert them to graph bin log and persist to Aerospike. Before persist to Aerospike, just like HBase right, has a write-ahead log, we also persist the graph bin log to offline. It's because currently for Aerospike, our haven't been in paper, it haven't been certified as SOR, system of record. So it's possible that the Aerospike crash, right? So in case Aerospike crash, we need the SOR, so it's just offline SOR. In case Aerospike crash, we can recover from offline. So another data pipeline is offline to online data pipeline. It serves for several purposes. One is backfill. Say if we want to add a new vertex, new edge, new properties. So the history data actually exists in offline. So we just generate the offline backfill data and push to online. Another use case is recovery, as I mentioned, right? And another third use case is we have a regular full refresh data, for example, monthly or biweekly, right? We can, in case Aerospike there's a right failures, we can eventually fix them, right? And another one more use case is the computer result from offline. For example, we have a bestseller flag, which is computed in offline. And we have jobs. We'll push this kind of computer result to online, to integrate with online, right? So those are actually for the offline. And another example is rebalance. Because when we add a new cluster, the traffic, both traffic and the data won't be balanced. So we use this data pipeline to rebalance the data. So this is a benchmark in GCP, Google Cloud. So we have a framework of benchmark, and we predefine the queries. Typically, they are, most of them are 2 hops query. And you can look at the performance. They're pretty fast. And if we look at like, if the query need to visit like hundreds of vertexes, the average latency just within 20 milliseconds. Pretty fast. And pretty scalable because thanks for async. And this is our benchmark in production. So you can, I'm not sure you can see it clearly, the write performance. It's just within 100 milliseconds, very fast. And for the read, it's a 2 hops query, and usually it's need to access hundreds of vertices. So the performance is peanut latency within 150 milliseconds. Very impressive. Right. So that's all for my. Cassandra, built by Java, has GC issue, right?
I know the problems. I just wonder, is it twice? Is it 10 times faster? Like, what's the main?
We don't have apple-to-apple comparison, but we are sure that the latency should be second level.
You mentioned 100 milliseconds, but in the previous slide you talked about 100,000 operations per second.
Yeah, it's a great question. I know. So first, the benchmark actually is in Google Cloud. Google Cloud, the network is pretty good. Because we support a different availability zone, our people private cloud. There's some additional overhead for the network.
I think I'll add to that is the type of instances we're using in Google Cloud is pretty cheap ones, where it's all normal persistent SSDs, not the NVMe ones. But as we move forward to production, it's all NVMEs.
The obvious question, are you planning on open sourcing this? Some of it, and
Yeah.
like things like, I mean, I don't know what you're using, but say something like Janus Graph is it's out there, it's open source, a fork of Titan. Yours is more custom made. Does it make sense, or you're not allowed to, or is it just too tightly integrated with your own stuff?
Yeah, good question. Actually, first, it's a very generic solution. It's a homemade. It's a very generic. Second is, yes, we do have the potential to open source it, because in our code base we have two repository. One is the common repository without any PayPal dependencies, and another is with PayPal dependency. Right? We separate them. So the problem is for us is it a priority for us to open source it? Or do we have enough resource to open source it? Because for open source, there's additional overhead. Yeah, it has potential.
And also the experience from what we have seen is, it's all trying to cater to the masses within the company as in general. But as we go and mature ourselves and we see potential that everybody likes it and we can also push it out. There has been many different projects, and I'm assuming, like Bruce is mentioning, as we mature, as we see that we can get contributions from outside as well, we definitely, I think, will be in considerations.
Yeah.
So you touched upon this about the edge modeling. You said something like edges are stored with the vertex. Is that right, or do you have a separate?
Right.
Okay, that's how it's done. So the schema specifies the kind of relationships you're allowed to have. So you can't just do merchant to this or strange entity relationships. So does your schema enforces the relationships as well?
Yeah.
Okay.
Yeah. Configuration and mandate-driven, right? The principle, design principle.
Okay.
Yes.
And you only support second degree. That's the performance.
Yeah.
You can't do third degree.
Two hops, 3 hops. You mean?
Yeah, 3 hops.
Yeah, definitely. There's no limitation for solution itself, but it's just the limitation for the SLA for online application, right?
And to add to that, there could be policies where you can always say 3 hops is this SLA, 4 hops is this, but there is also possibilities of hotkeys that can happen. Then we'll have to data model it accordingly to make sure that we are compliant with SLA plus. So the complexities will just go up as we go further with the higher hops.
Yeah, we have for online. We do provide the guideline for online application integration, right? For example, for one query, we can limit, instead of limit the hops, we can limit the number of vertex access, right? Essentially, right? Time out.
Like even a top 10, kind of one, top 1,000.
Yeah, actually, when we build the graph for written graph, right, we do support the limitation for the edge. So default, for example, for risk, right? So maybe recent 10 or sorry, 1,000 relationship is good enough. So you can ignore the oldest one, right?
Yeah, and you know, even if we want to do higher number of hops, the system itself is capable because there is a lot of throughput that we can, you know, harvest from the database and the hardware. We're just making sure that our SLAs are tight and it's always consistent.
Right. Another is you can see the design, right? So the Gremlin, this solution actually not only for online database, also can support the offline graph as well. So only difference is offline may have more data, right? And it may take, how to say, the data object size will be larger than online. The solution will be the same.
What is the read and write request rate for the collection? The latency number you present. So what is the read and write request rate?
Currently, by the end of Q1, we released our MVP. So now it's a 100% ramp up already. So currently, for QPS, it's like 1 to 2 query per second. But definitely, our solution can support much more, right? But the current the business is only like for each server, there's only 1 to 2 query per second. That's the current state.
And Bruce, this is on the client side.
At the client side. It's a client side.
So, and just to expand on that, the client itself, we would have hundreds of nodes.
Yeah, in our benchmark, actually, for 2 query, because thanks for the async solution, right? We can support like 3,000 to 4,000 query per second without any problem, and the SLA still, the latency is still acceptable. So solution is highly scalable.
It's really client that we need to scale. As we scale client, obviously we'll have multiple hop queries getting into the database, which as of now, I think we probably are in 10%, 20% utilization. We have a long way that we can go. But if you want to scale, we go horizontal client scale.
We're ramping up the use cases.
What about the latency? What are the average latencies?
Latency for query?
For a read or a write?
Yeah, for read query. It's the P99 latency you can see here. Sorry, 150 milliseconds. This P99.
So I think the observation has been consistently that as we look at 95 to 99, the last portion is obviously much higher. But in general, if you look at all the individual queries, if you just want to parse it out and look at what did key value look like, it's all NVMe. So we are, pretty much mixed, kind of a mode NVMEs that we choose. They're pretty fast. So it's all millisecond or under in a 95th percentile, 99th percentile, 1 or 2 milliseconds. We design it accordingly. But there could be complications with queries that's coming in. So that's where those numbers could go up.
So for like not 99%, what's your average?
Average.
For a query,
Average is, let me see. Sorry. 40 milliseconds, within 40 milliseconds.
So by the way, this slide was put at the last minute.
I think my eyes are bad. I can't read any of
We couldn't share a lot of information from PayPal, so we wanted to intentionally do this.
Actually, the original version contains more information, but eventually.
We got trimmed a lot.
Any other question?
Okay, so why not Aerospike under Janus graph?
It's possible. It's possible.
There actually is a project out there now.
Yeah.
I was just curious, like, why you specifically you chose and you
But-
analyzed the different options.
But it's possible, but we need to do a lot of optimization for GNS graph.
So you're saying you looked at Tiger Graph as a model for where you want to be. You already have like an Aerospike system that works well for you. So
Yeah.
you're like, we're going to emulate what they do rather than look at what Janus Graph does because they're not in the same
Yeah.
category.
We do have internal discussion for that solution as well. So for GNS graph, it do support the storage engine abstraction, but the data access pattern is not good. For example, it's a read-write as a whole, right? KV storage. So in the end, we decided that to directly integrate with Gremlin is not hard. So we just built our own solution on top of Gremlin. Multi-records, what does it mean?
So it's based on Aerospike, and Aerospike only have convention based on each record. So
Yeah. Currently, the first use case is technically there's no problem, but currently first use case it's a logic graph instead of transaction graph. So it's not a transaction graph yet. So yeah, we will build it. It's in the plan.
And I think that's a good point. If we were to look at transactionality, from the get-go, we have the consideration of consistency being relaxed. If we were to continue with that, obviously there might be other issues if we were to consider it as consistent. Here we're taking that as a relaxed mode, but trying to get and harvest much more throughput and low latency from the system.
Just one more question. What's your overall goal for the P50, P95? Are you trying to get below 40 milliseconds for your average? Do you have a specific target in mind? Because I'm assuming some use cases can't be done until that latency is cut down. But do you have a particular target in mind?
So basically, it's a business requirement, right? The SLA requirement. So we just provide them guideline. Say if you want to this kind of SLA requirement, how many vertex you need to access. Based on that, so we can define the data model and set the limitation for the traversal. For Gremlin, actually, it's very flexible. For each hop, it supports the limitation, global limitation, and the local limitation. So we can apply the very strict limitation for the traversal.
And I think to add to that, we have similar patterns where we have strict SLA saying 50 milliseconds for an end-to-end execution. Now, as Bruce just mentioned, that there could be very different requirements from different units who are working on different parts of this. If we were to consider that, then obviously we'll have to slice our number of hops into certain numbers and say this is the SLA, and we can consistently get at 99 percentile. So far, I think we have tried harvesting as much, so average is looking okay. But an end-to-end experience means 99 plus has to be a certain number.
Yeah. So for example, denial of payment attacks against a merchant, you need to be less than.
And I think that's why Bruce was highlighting that this is considered as real-time processing, right? And that's where the challenge will be, that how much real-time can we keep up with in over time.
Last one for me, I promise. How do you integrate currently with Spark? I saw that the updates are done through Spark, I think, on your graph, but how do you?
Yeah, Spark support GraphX, right? So support GraphX, and the GraphX can integrate with Gremlin. So because we support a standard Gremlin query, traversal, compute, so it's not a problem.
So people can use Spark to query this system directly?
Yeah, it's an existing capability for SparkX or GraphX, right? Because we support a standard Gremlin, it's not a problem.
And for other people, they use like a Java to using Tinkerpop or something to do this, if they want a different interface, or is it all done by Spark?
Yeah, currently, for some use cases, we need it, but currently we haven't bring it to production yet, but it's potential. Yeah.
All right, very good. Thank you. Thanks, everyone.
Thank you.